polar coordinates is like the other kind of coordinates. You've learned about rectangular coordinates that have x and y in them. And polar coordinates are a little bit different. Sometimes they're just what you need, and they're really good for describing things that are round, or round-ish, or best described referenced to the origin and the distance to the origin. Polar coordinates are also a lot of fun. So let's go explore those polar coordinates. I suppose I ought to go prepared though, because you know, polar coordinates can be pretty cold. So I'm going to need a nice warm coat. I've got my gloves. And just remember, when you're evaluating polar coordinates, sometimes it can be kind of a little bit intimidating, but it's okay.
Dad, it's still summer.
Unlike rectangular coordinates, where to find the coordinates of a point, what you need to do is measure the horizontal, the x, and you need to measure the vertical, the y, to find that location of the point. In polar coordinates, we do something a little bit differently. We start at the origin. And once we start at the origin, we pick a direction, an angle. And with that direction and angle, then we measure directly to the point and measure the distance to the point. So instead of x and y, we have r, radius, and theta, angle. A little bit more precisely, polar coordinates starts out with the same plane that you're used to, the horizontal and vertical axes. We can label them as x and y, as usual. But the polar coordinates, coordinate of a point, read out in r and theta, where r is the distance to the origin, and theta is the angle in radians from the x-axis measured counterclockwise. Okay, now if you want to convert between polar coordinates and rectangular coordinates, all you need to do is realize that what we've got going on here is a right triangle. That right triangle has a hypotenuse of r, and the two legs are x and y for the x and y coordinates of this point. And using the usual trig formulas, you'll find out that x is r times cosine of theta, and y is equal to r times sine of theta. So this will take you from polar to rectangular. If you want to go the other way, you could totally do that. You just need to solve these two formulas for r and theta. The r coordinate's easy to find. That's just the square root of x squared plus y squared, the length of the hypotenuse. Theta's a little more tricky. If you look at the way that I've drawn this particular point in the first quadrant, you'd say, well, theta should be the inverse tangent of y over x. True enough, that works provided both x and y are positive, but there's a bunch of different conditions, a bunch of different cases. So it's the inverse tangent y over x if x and y are both positive. Of course, if you go beyond that, if you go to the second quadrant, you will find something that will require a little bit of modification. And so in particular, the thing to do then is to add 2 pi. Or rather than adding 2 pi, you want to subtract the quantity from pi. So if my point instead is over here, we want the theta angle to be this blue angle here, but the arctangent of y and x will give you this theta here. So the way to do this, say pi minus inverse tangent of y over negative x. If x is less than 0, y is greater than 0. But if you look at this formula, you'll notice I've got a minus in the denominator. The tangent function is an odd function, so that minus comes out. And now, on the other hand, if I'm down below, down here, in the third quadrant, I'll go all the way around, and now I've got a negative x and a negative y. So there's my x and my y. And so, same kind of idea. I'll want pi minus tan inverse negative y, negative x. Of course, those guys cancel. And finally, if you're back in the first quadrant again, down here, you can either take the negative answer that you've gotten, so the theta will read negative like that, which is perfectly fine. But if that bothers you, you can add 2 pi. X is positive and y is negative. Now this is kind of awkward, but it is what it is. If you happen to be using a computer, it's been around since the 60s, ancient Fortran programming language and many others have a function called atan2 that will do all of this. And it'll handle the situations where you're on the axes as well. I haven't filled in what happens if x is equal to 0 or y is equal to 0. Those are cases that'll come out as multiples of pi over 2. I think you could figure those guys out yourself. Okay, so what are some functions written out in polar coordinates? What curves do you get? Well, perhaps the easiest one is r is equal to 1. What does that look like? Well, r equals 1 should be a circle centered at the origin. And indeed, circle centered at the origin with radius 1 gives you r equals 1. And of course, r equals anything will be a circle centered with radius anything centered at the origin. Similarly, if you pick theta equals something, you'll get a line segment that ends at the origin. So here is theta equals 1. It's 1 radian measured off of the x-axis counterclockwise. But if you try something a little more complicated, like r equals cosine theta, that's perhaps a little bit mysterious. What is this guy? Well, let's write it out in rectangular coordinates. Where the r is being substituted into the formula. Okay, well this first one is cosine theta squared. This second one is 1/2 sine 2 theta. I can use a trig identity for cosine. And the thing to notice is that now I'm parametrizing. This is the parametric equation for a circle of radius 1/2 centered at the point x equals 1/2, y equals 0. And indeed, that is in fact what happens. Okay. So what about something that's a little bit fancier? What about r equals cosine 7 theta? Well, you'd be right in suspecting that this thing has got some kind of structure that involves a 7, some kind of 7-fold symmetry. So notice if theta is equal to, I don't know, theta prime plus 2 pi over 7, curve will be the same. Because what will end up happening is everything will be rotated by 2 pi over 7, and the argument to the cosine will get an additional 2 pi added in, and cosine is periodic with period 2 pi. So this is something that's got a 7-fold symmetry. And indeed, what you end up with is something called a rose, and indeed it's got 7 petals, it's got 7-fold symmetry, so if you rotate this 2 pi over 7 radians, you'll get the same plot. It's called a rose because, well, it kind of looks a bit like a rose. Finally, for our last curve, let's look at r equals 1 minus sine of theta. This one's a little tricky. When theta is equal to 0, so I'm on the positive x-axis, I'm at 1. So let's say I'm right here at 1. When I get to theta equals pi over 2, so I'm on the positive y-axis, then it's 1 minus 1, it's 0. And everywhere in between is positive, so the radius has got to decrease as I'm moving around. Now, sine is symmetric around there, and around that point, because if I plot the sine function, let's plot the sine function, this is theta, this is sine of theta. So we were just finding that this point here is this point here, this point here is actually this point here. So the curve is symmetric across this line. So what that means is that we'll end up with something that looks pretty much symmetric up to that point. So that's now here. Now after this point, so for theta is down in this segment, sine of theta is negative, so I'm subtracting in the formula here 1 minus a negative number, i.e. 1 plus a positive number, so my radius will actually get bigger, and it gets to a maximum right down here at 3 pi over 2. 3 pi over 2 is the negative y-axis, and sine of theta has a value of negative 1 there, so the r is going to be 2. So we'll end up with a function that looks a bit like this. This shape has a name. It's kind of heart-shaped, and it's called a cardioid. There are lots of cardioids. You can change that one, or change the factor in front of the sine, or maybe change the factor in front of the argument of the sine on the theta, and get different kinds of cardioids. I encourage you to play with them, and maybe as a result, this heart will say, I love polar coordinates. Maybe.